So here I'm going to just quickly walk through using matrices to solve linear systems of equations. So at this point you should be comfortable solving matrix equations from our prior lesson and worksheet. And so now I'm going to show you our first application of matrices, which is how to use them to solve systems of equations. And so to motivate this, I have this first question on the worksheet, which is just multiplying out two matrices. So let's go ahead and do that. Okay, so here I've just written the matrices in our format that we like for multiplying them, and I'm going to give myself enough space here. And again, just remember how we multiply vectors. We do basically dot products of, multiply matrices, we do dot products of vectors here. And so in this case, we do 5 times x, which is 5x, plus 4 times y. So our first entry here is going to be 5x plus 4y. And our second entry is going to be this row dot product with this column. And that's 2x plus 3y. And so notice here we have a 2 by 1 matrix, which is expected because we started off here with a 2 by 2 and here with a 2 by 1. And so we knew that we were going to end up with a 2 by 1 matrix. And so I'm asking here, does anything about this this result of this matrix product remind you of a system of equations? So if we stare at this long enough, well, it certainly looks like it would be the start of a system of equations. There's no equal sign, but when we see a system of equations, it normally looks, something like this, but it would just be missing these equal components. And so that's the motivation behind why matrix multiplication might get us something that looks like a system of equations. So next, let's move down to question 2, where it says, now let's actually write the following system of equations using a matrix equation of the form. So there's several matrix equations that we could use here, but notice how what we're looking for is matrix A times matrix X equals matrix B. So the first question was trying to lead you in this direction. If we look at this side of the equations, it certainly looks like we could get it to look like that if we go back up and just use this multiplication. So that's actually what we're going to do. We're going to write the left side of the equation here just as 5, 2, 4, 3 times this matrix xy. So we're going to think of this matrix as A, this matrix as X, and we want to write this as a matrix equation, so we need another matrix here, B. Well, just let's copy the result from up top. So all I've done here is just multiplied out these two matrices, which is just the same thing we did up here in number 1. That's the result. So now we see that this first element of this matrix, 5x plus 4y, well, in the system of equations, we want that to equal 2. So let's set that equal to another matrix, which will be 2 by 1, where the top entry is minus 2. So then we have the situation here where this 5x plus 4y is going to equal negative 2, because the corresponding elements of matrices, if they're equal, are equal. And then the second piece here, as we underline this in green, we have 2x plus 3y. Well, based on this system here, we want that to equal negative 5. Sorry, let me put that in blue here. Negative 5. And I'll underline it in green. So now we've basically written this as a matrix equation. So I'm going to come back up here and just complete this off. Negative 2 and a negative 5. So you can see here that this has an exact correspondence between the system of equations. If I go ahead and execute the multiplication on the left side, I will get and set it equal to the right side. And when I do that, when I set the elements equal, I'll have this system exactly represented here with A, X, and B. Notice what these entries in this matrix are. This A matrix is going to be the coefficients of the system. And it's important to have those in order. Notice how the X's and Y's in order over here. This X matrix is going to be the variables. And then this B matrix is going to be this column here. I don't know if it has an exact name, but I'll call it, what it equals. And so that's how we're going to set up this matrix. So hopefully you see why we're going to go ahead and do this. Because we've solved matrix equations, right now we have this thing in the form AX equals B. Let's remember how we're going to solve that kind of equation. We're going to left multiply both sides by the inverse of A. Remember, it's important to multiply on the same sides. We pick the left side because we want this to cancel out and become the identity matrix. And so this will become IX equals A inverse times B, or X equals A inverse times B. We'll look at this equation. Because this X matrix is our variables, we can just, if we go ahead and multiply these two matrices out, we'll get the answer. And that's what we're doing in step 3 on this sheet. So here on number 3, I've just copied down what we had from number 2. This is our original system expressed in matrix form, in the form A, matrix A times matrix X equals matrix B. And we know that when we multiplied that out, we would be representing the system. This represents the solution for X. And again, X, all we did here is multiply both sides by this A inverse again to get X equals A inverse times B. So since we've now solved this thing for X, all we have to do is execute this matrix operation here to solve for X and Y. So let's remember what A inverse is. To get the inverse of A, the first step is we need the determinant. So the determinant of A is going to be 5 times 3, this diagonal, 5 times 3 minus 4 times 2, which equals 7. So we know we're going to have a 1/7 out in front. And then we just do our rearrangement of the terms here. So 5 and 3 are going to switch positions on the main diagonal. The other diagonal is going to, they're going to stay, but we're going to switch the signs. And so there's our matrix for the inverse. And then we just need to multiply this guy by B, -2, -5. So this expression here is A inverse, and this expression here is B. So I'm just going to go ahead, and rather than multiply this scalar into this matrix, I'm going to keep it off to the side just because it's going to make the math a little easier. I'm going to go ahead and multiply these matrices. We know the result of this matrix, so we're going to have a 1/7 out in front, and this matrix is going to be a 2×1 matrix. And then we'll just fill this in by doing the correct dot product. So the first entry is going to be 3 times -2, -6, plus -4 times -5, which is a +20. So we're going to have 14 in the top position here. And then the bottom position is -2 times -2, which is +4, plus -25, which is -21. And then we'll just multiply through by the 1/7 factor now. So 1/7 times 14 is 2. 1/7 times -21 is -3. And we have our answer here. So let's remind ourselves that X equals the vector, or the matrix I should say, which is like a column vector, XY, which equals 2 and -3. So the way to interpret this then is that X equals -2 and Y equals -3. So we've gone ahead and solved the equation. Our solution is 2, -3. Okay, so now just to finish this off, I'm going to go ahead and set up the ones on the back side of the page, which are larger systems. And this is where the power of the matrix approach really comes into play, because we can solve larger systems. So here we have a system of 3×3, a 3×3 system with 3 variables and 3 equations and 3 unknowns. And just like before, the first step is we want to write this as a excuse me, matrix equation of the form A times X equals B, where A is going to be the coefficients, this is going to be our variables, and this is going to be the equals. So let's go ahead and set this up. We have our coefficient matrix here, and we're just going to drop in all these numbers. 2, negative 1, 1, 3, 2, negative 4. So 3, 2, negative 4. 1, negative 3, negative 2. And there's our coefficients. We have 3 by 3, so there should be 9 entries in our matrix. We're good. Now, oops. Now we'll just write our variable matrix, which is going to be here x, y, and z. And that's going to equal the equals matrix, the 3, 23, and 14. If we wanted, we could multiply one of this top row out just to make sure it looks correct. So 2 times x minus 1 times y plus 1 times z looks like it's going to give us that equation. So it looks like we've got it all set up correctly. And then to solve this thing, we just need to get this by itself, the variable matrix. And we're just going to left multiply by the inverse to get rid of it. We want to get rid of the inverse over here. So we're going to go ahead and do that. So I went ahead and wrote this all out just so you can see what's going on, but you wouldn't have to write this all again on your own paper. So let's just see. All I did was I took the inverse here and I left multiplied both sides by the inverse. And this piece was here, and then this was what's here. So I left multiplied by the inverse so that when these are going to group and go away, they're going to turn into the identity matrix. And so we'll just be left with x, y, and z is going to equal the result of this multiplication. And this is one where you can just go ahead and put that in your calculator. The way you do that is when you enter the matrix, you use the caret to the -1 sign to get the inverse, and it'll just give it to you. And then you go ahead and multiply it by that matrix. I don't have my calculator app stored on this computer where I'm doing the video, so I can't show you. And then as shown up here, when you do this, you should get a vector that's 3, -1, -4. So the answer here will be 3, -1, -4, which is the result of doing this on the calculator. And again, we don't actually, I had never even told you how to do inverses of 3 by 3 matrices, so you have to do this one on the calculator to get it done. And then the last one here, again, the setup is just about identical. We're going to put it in the form a x equals b. Here's even a bigger one. It's a 4 by 4. This is a common way to write variables when you have lots of variables in your system. Instead of using x, y's, and z's, it starts to get messy when you have too many variables. We're just going to use a single variable name with subscript so it's clear which one we're talking about. So here you want to think of x1 as x, maybe x2 as y, x3 as z, and then x4 as w. But this is a common way to go ahead and do that. So we're just going to go ahead and write this matrix equation, and now it's going to be a 4 by 4 matrix. I'm just going to pause it here and write it out so you don't have to sit here and watch me write it. Alright, so here I've written everything out, and one thing again to make sure of is that everything's in the correct order here. Like if these things were actually rearranged, you'd have to get them in the right order so that all the x's are lined up, all the x2s are lined up, x3s, etc. And the other thing I wanted to point out is notice how there's some missing terms here. And we have to reflect that appropriately in our matrix with a 0 coefficient, because this is almost as if there was a 0x1 there. So you can see down here we have a 0 in that position, and we have a 0 in that position in the coefficient matrix. But then to solve this, you're just going to take the inverse of this guy, which is a. So take the inverse of that times this matrix here, b. And that'll give you a 4 by 1 matrix which has these values in it, the corresponding values, x1, x2, etc. And again, the way you put this in your calculator is you would enter a 4 by 4 matrix and raise it to the -1 power to get the inverse, and then multiply it by this matrix here, and then we're left with that variable matrix, which would be x1, x2, x3, and x4.